So let us try to understand the intuition using this toy example. Say there are two variables, quiz 1 and quiz 2. And the marks that you have secured on quiz 1 is plotted on this axis. And the marks that you have secured on quiz 2 is plotted on this axis. And seems like there is a positive correlation between quiz 1 and quiz 2. The idea of principal component is, can we come up with principal components which would capture more information than quiz 1 alone or quiz 2 alone? Okay, the idea here is, can we come up with a principal component, a new variable, which would capture more information than quiz 1 alone or quiz 2 alone? Say quiz 1 is capturing your IQ level. It's trying to capture your hard work. Say it is also trying to capture your discipline. Say it's also capturing your class attendance. Say all these are captured intuitively by your quiz 1 marks. Of course, if you're getting good marks, that can be attributed to your IQ level, that can be attributed to your hard work, your discipline, your attendance, so on and so forth. Say there is quiz 2. The marks that are attained by students in quiz 2 probably will also capture the IQ level, hard work, discipline, attendance, so on and so forth. So there is some amount of overlapping information which is getting captured by a quiz 1 and quiz 2. The idea behind principal components is to come up with a new variable or a new axis altogether which does not capture any overlapping information. Right? And here variance is synonymous to information capture. For example, if all of the students have scored 8 out of 10, all the 10 students have scored 8 out of 10, then there is no variance absolutely. And what information would be captured? Absolutely no information, because all students are the same. However, if there is a difference, if one student scores 8 out of 10, another student scores 4 out of 10, another student scores 5 out of 10, now I know that there is some variation among the students. The moment you have variation, you can capture more information. From that perspective, more the variance captured by a principal component, better it is. More the variance captured, more is the information captured. The idea is simple. If all students are getting the same mark, you really cannot make out anything. You just know that everyone is getting that mark. But if there is some variance, you can speak about the different students. Right? You can speak about the smart students versus the weak students. Right? Suddenly your explaining power goes up. Okay. And say for quiz 1 and quiz 2, there is some overlapping information. What is that overlapping information? Both of these capture IQ, hard work, discipline, attendance, so on and so forth. So the idea here is, can we come up with a new axis altogether or a new dimension altogether which captures this overlapping information in a much better way so that there is no repetition of information? And that is what has given birth to principal components. So here is a new axis, new principal component. How do you draw that? I can draw a line like this, or we can draw a line like this, a red line, or you can draw another line like this, or you can draw a line like that. There are infinitely many lines which are possible for your principal component. But what is the idea? Idea is to have maximum variance, cover maximum number of data points. And how is that captured? So the distance between each and every data point is captured. So the distance between this point to this point is captured. The distance between this and this is captured. Right? In this way, the distance between each data point to this axis is captured. Once you calculate the distance of each data point to the line, you add all those distances, and wherever you get, the minimum distance, that is considered to be the accurate principal component. Yeah, that is how the principal component is captured. So you draw perpendiculars to this axis and say which axis gives you the least distance, basically, in this way. So from each data point you calculate the distance to the line, and wherever you get the least distance, that happens to be the best distance, basically. Alright, and since this is your principal component 1, quiz 1 and quiz 2 both put together no doubt would capture 100% of information, because these are the original variables. Now that we are doing some mathematical transformation, some information would be lost, obviously. And say this principal component 1 captures 90% of information. Alright, but this 90% information that is captured by principal component 1 is more than information captured by quiz 1 alone or quiz 2 alone. What about the rest of the 10% information? Rest of the 10% of information that you're going to capture should be unique. You should not again capture the information captured by principal component 1. You should capture the information which is not captured by principal component 1, and that's rest of the 10%. How would you do that? Only if the second principal component is orthogonal, perpendicular to the first principal component, we can say that the second principal component captures 10% unique information which is not captured by principal component 1. Okay. And within multiple linear regression, there is a concept of collinearity. What is collinearity? If the input variables are correlated, right? If there is some kind of linear relationship between your input variables, that's a collinearity problem. How do you get rid of that? Say quiz 1 and quiz 2 are getting involved in collinearity problem. You probably want to drop off one of those input variables and proceed with the other one. Instead of dropping that, you can use your principal component analysis, wherein you're going to get two principal components. Since you have two variables, you'll have two principal components, and these two are completely uncorrelated because they're orthogonal. Yep. So this is the intuition behind your principal component analysis. Now we will discuss about the preliminaries associated with principal component analysis.